So here's where we're going with this. Um, Recall that we were able to take any number in the Cartesian plane and, any point in the Cartesian plane and rewrite it in polar coordinates. So instead of writing it by the pair xy, we wrote it by the pair r theta. So just to recall how we did this, uh, let's suppose we have the number negative 2 comma 2 root 3, which exists at roughly the location that I've shown it on in this graph on the left side. So recall how we actually converted this into polar coordinates. What we did is we said that r is equal to the square root of x squared plus y squared, which in this case is going to be the square root of negative 2 squared plus 2 root 3 squared. That equals square root of 4 plus 12, or 16, which is 4. So what we know is that this point is going to have, when we put it in polar coordinates, it's going to have a radius of 4, and its angle theta would be arctangent of y over x, and then since we're on the left side of the plane, recall there's that very complicated formula for finding theta. Since we have x is less than 0, we're going to have to add pi to whatever arctangent gives us. You can go back to that lecture to see why that's true. So this is going to be arctangent of, let's see, y is 2 root 3 over negative 2 plus pi, which equals arctangent of negative root 3 plus pi. That gave us arctangent of negative root 3 is negative pi over 3. And add pi to that, and you get 2 pi over 3. So that's the angle. So this point in polar form is 4 comma 2 pi over 3. Now, interesting thing to note here is that this number, negative 2, this point, negative 2 to root 3, can be rewritten. I'll switch back to purple for that. We can write that negative 2 to root 3 is equal to 4 cosine of 2 pi over 3, comma 4 sine of 2 pi over 3. In other words, once we have the r and the theta, the original point is r cosine theta comma r sine theta. And we saw that when we converted in the other direction. We saw that x is equal to r cosine theta, y is equal to r sine theta. So cosine of 2 pi over 3 is actually negative 1/2, and sine of 2 pi over 3 is root 3 over 2. So we see is when we multiply 4 by those, you get 4 times negative 1/2 gives us negative 2. 4 times root 3 over 2 gives us 2 times root 3. So these points, so this expression is actually, this one is actually equivalent to this one and this one. Okay, so how does this map onto what we know about complex numbers in the complex plane? Let's do it on this side. So let's suppose that I have the complex number z equals negative 2 plus 2 root 3 I. So of course we would map that to exactly the same point in the complex plane. In other words, if I call this the xy plane and this is the real imaginary plane, like that, 3, 4, there we go. I put this point here, and clearly this point is going to be negative 2 plus 2 root 3 I in that plane. So that means is that since we know that, let me just go back here, we know that negative 2 equals 4 cosine 2 pi over 3, and 2 root 3 equals 4 sine of 2 pi over 3. That means that I can rewrite this number down here as z equals 4 cosine 2 pi over 3 plus 4 sine of 2 pi over 3 I, where this, of course, is a and this is b. Now, so first of all, what this demonstrates is that I should be able to describe a point in the complex plane by the pair r and theta, just the same as I can for a point in the Cartesian plane, since it's really the same plane. Now, before I go on, what I want to do is I want to factor something out here. I want to rewrite this as 4 times cosine 2 pi over 3 plus sine 2 pi over 3 I, or actually, I'm going to rewrite it in different order, I sine of 2 pi over 3, like that. Okay, now this doesn't look like I've done anything really interesting, but let's look at the structure of this number that I've written. First of all, it's got outside here, it has the radius of the complex number on the complex plane, so in other words, that's going to be r, the radius, the distance to the origin. And then in here, I have two instances of the same angle. So this is an angle. These actually have a special name. We call r is the modulus. And this angle, which is theta, we call theta, is called the argument. That's the name we use for r and theta when we're talking about complex numbers. But what I want you to do is focus on this expression here, cosine of theta plus I sine theta. And in the next segment, just be prepared to have your mind blown.